Okay, so after we've maximized the amount of precipitate, to the best we can, we're going to filter out the precipitate. And so hopefully the oxalic acid and the potassium oxalate get washed into the supernatant here. We're going to use a Buchner funnel for this, which is this large funnel. The Buchner funnels are for getting higher volumes of precipitate here. We're not going to use a water aspirator. This is a cheap way for generating a vacuum, but it's a huge waste of water. So we don't need a vacuum pump. We have a vacuum pump, a mechanical vacuum pump here. And we have the gas tap and the vacuum tap at each station. So you can connect this directly to our vacuum pump. But the problem is if we get water, if any water gets, or any liquid gets sucked into the vacuum pump, liquids are not compressible. And so what will happen is it will destroy our vacuum pump. So we can't afford to get any water from the pump. That means we have to make sure we trap any water that accidentally gets sucked. This is a filter flask. And a filter flask is recognizable because it has a sidearm. This sidearm is for vacuum attachment. So let's say some liquid gets accidentally sucked into the sidearm. We don't want this to go straight into the vacuum. We want this liquid to get stopped in the trap. But this is something I didn't notice before. There's something wrong with this. Do you see what's wrong with this? So the liquid, if it gets sucked into the vacuum here, we don't want it to get sucked into the vacuum pump, so we want to trap the liquid in this liquid trap. Yeah, do you see it? It's backwards. This is wrong, because what's going to happen is I'm going to just build up a little pool of water here, and as I build up a little pool of water, that's going to get sucked into this tube and then destroy our vacuum pump. So this is backward. So the person who drew this is probably a good graphic artist, but probably not a chemist. And so the short tube should go on this side, and the long tube should go on this side here. That way, the water is going to get dumped into here, and we can build up a pretty high level of water before it gets full and then sucked into the vacuum. Does that make sense? Yeah. And so this is backwards, but that's all right. And so normally what happens is this gets filled up. People are doing a lot of rinsing. If it starts getting filled up, you have to remove this and dump the supernatant. Sometimes you save the supernatant, sometimes you dump it. You have to be very careful depending on the experiment. Sometimes the precipitate's garbage and the supernatant's what we keep. Other times the supernatant's garbage and we keep the precipitate. And yet other times we keep both, the supernatant and the precipitate. And so this is why it's important to read through the entire experiment to make sure you don't throw away the wrong stuff. People end up throwing away the wrong stuff all the time. For us, the supernatant is garbage. So what I usually do is I keep a big waste beaker at the work lab station, and then at the end of the lab period, I'll go and dump it into the waste jug. Our waste jug's in the last hood along the back wall there. Okay, so we're going to filter out our complex precipitate here, this green-black precipitate, and then we're going to wash the crystals. The crystals are going to be contaminated with a solution of oxalic acid, potassium oxalate, whatever else. And so we're going to wash it, but we're not going to wash it with water. What are we going to wash it with? Ethanol. And so you want to thoroughly wash this. Now, when we do the reaction, it's hard to transfer the precipitate over. So what I recommend is use the wash solution to help you transfer the crystals from the beaker into the filter, the Buchner funnel. And that'll help you transfer. You don't have to worry about getting every single crystal transferred over. This lab, you aren't graded on yield, percent yield. So you aren't trying to get 100% yield. You're more graded on the quality of the crystals. you get. And so if you lose some, that's okay. We just want good quality crystals, not quantity necessarily. It's nice to have both, though. All right, so we'll transfer the crystals over. Now, after we do this, our initial wash is going to be 50% ethanol. We have 50% ethanol over there. Our final wash will be 95% ethanol. Now, the sequence, while we're doing that, is this. 50% ethanol is 50% water, 50% ethanol. And so there's going to be a lot of water left. And the purpose of the 95% ethanol is to wash the water off. Water loves ethanol. And so the water will go into the ethanol and then be drained into the flask here and discarded into waste. But if we have mostly ethanol here, 95% ethanol evaporates quickly. And so we do this, the 95% ethanol is to wash the water off and to allow for rapid drying of the crystals, because ethanol, especially 95% ethanol, vaporizes quite rapidly. However, we're not going to do that. What we're going to do is we're going to try to get even better quality crystals. Normally, when you grow crystals, what do you want? Do you want a lot of little baby crystals, or do you want a few big crystals? You want big crystals. The bigger the crystals, the better, because to form a big crystal lattice, things have to be well ordered. And if impurities get into the crystal, it screws up the packing of it, and you can't grow big crystals. And so the bigger crystals you grow, that has to lock out any kinds of contaminants or impurities. And so normally when people want really high purity, they want one single giant crystal. A single crystal, that's going to be high purity. So when we do the initial precipitation, we're cooling it in an ice bath, we're adding the ethanol to it, we're probably going to generate a whole bunch of little crystals. And so what we're going to do is we're going to take these little crystals. Some of you might get some bigger crystals, but little to medium crystals. What we're going to do with those crystals is we're going to redissolve it and then try to reprecipitate it. But in this second round, we're going to try to reprecipitate it, growing bigger crystals. So these should be a lot purer because we've washed off the contaminants. And so we should have pretty high purity crystals here, and then we're going to further purify it by recrystallization. And so let's talk about the recrystallization step here. What you're going to do is you're going to carefully scrape the crystals back into a beaker, a clean beaker. And so we'll transfer the crystals back into a beaker here. We don't have to dry these or do anything. And then we're going to add a minimum of water to redissolve it. So I don't want to use too much water here. It's going to make it hard to precipitate out. And then I'm going to add ethanol. And so what I'll do is I'll put a minimum of water here. I'm going to get a solution. And so all my crystals should dissolve. And then I will add ethanol to this, the 95% ethanol. And initially I'll add 10 milliliters. If I don't see any precipitate, or if I do see, I'll add the 10 milliliters slowly. If I start to see precipitation, then I'll slow it down even more or maybe stop. What I want to do is I want to add enough ethanol so that maybe a few crystals precipitate and then leave it. I don't want to add a bunch of ethanol to maximize the amount of precipitate. I want to add enough ethanol to start. These are going to be my seed crystals. So I want to just kind of generate some crystals that can grow. And it's a compromise, I could have lots of baby crystals that don't grow so big, or I can have a few crystals that grow big. It depends on how I do this. So I want to be careful. If I don't see much in the way of precipitation, then I'll keep adding ethanol until I get to about the same volume. So let's say I added 100 milliliters of water. I'm going to add about 100 milliliters of ethanol. Okay, if I don't see much crystallization. If I see a lot of crystallization, I'll probably stop adding ethanol and forcing crystallization. Does that make sense? All right, 10 milliliters plus. And then what we're going to do is we're going to cover this. You're either going to cover this with a watch glass or a beaker. Just get a big beaker and invert it over the little beaker. This is to prevent stuff from falling in there. It's also to promote slow evaporation of ethanol and water. And then leave in drawer. And then we're going to let the crystals grow over the weekend. Hopefully we get nice big crystals by the time we come back on Tuesday. If we don't, then we'll just continue letting the crystals grow slowly. Okay? All right. Now, we do have weighing paper back there. We could use, you have two choices. One, you could use weighing paper to weigh your solids, like oxalic acid and potassium oxalate. The weighing paper you just fold in half, and then fold it in half again, the same direction, to make a little boat. And then you can tear this and transfer it over. Or you can just bring a beaker, tear the beaker. The beaker doesn't have to be dry. And we're adding water anyway. The amounts don't have to be exact, just approximate, but you should record the numbers to as many sig figs as possible. The dichromate, though, I'd rather you not use paper because the dichromate will start to react with the paper. And, it's slow because, solid to solid, you don't get collisions. And so solids react slowly, typically with other solids. Instead, for the dichromate, I just put it in a beaker. It's probably better a dry beaker for that, in case you overshoot it or something, a clean, dry beaker. And you don't want something too small because then it's hard to get it into the mouth of the beaker. You want a bigger beaker. And then you can always use a little bit of water to transfer it over. It's fine. Okay, any questions on this? All right, the next thing we're going to do is we're going to take a look at this safety video here. This is one I found from UCSD.
I don't know. When I took my first lab, I had similar concerns, but once you understand the logic behind these rules, it'll be a lot clearer.
Do you think though that a lot of these rules are a waste of time and will slow us down?
Don't worry about that. You can get seriously hurt, and that will take more time for that. I'll walk you through it.
Alright, thanks.
Hey everyone! My name is Kayla and I'll be your TA for this quarter. Let's go on into the lab. Alright everyone, just come on in the lab. Go ahead and put your backpacks in addition to the people so that way no one will trip over them. And grab your protective gear and come on to
That's lessons.
Oh, thanks. I got them from a research lab.
Yeah, so dorky. I got one from my dad's workshop. I thought it would save a couple bucks.
I think we have splash goggles for the first part of this lab because we're going to be using concentrated sodium hydroxide solution, and that stuff is nasty if it gets into your attic.
Hey, are you guys ready to get started?
All of us. I just noticed my safety glasses don't give me enough protection, so I'll go get my goggles.
Okay. I'm afraid that yours aren't good either. See the ventils? They won't protect you against the splash of liquid. You need chemical splash goggles that will give you indirect venting. Why don't you go ahead and grab another pair and come on back?
Okay.
Before we get started, I'll just point out the location of the safety equipment at the lab. Because you'll all be wearing your protective gear, you most likely won't need to use it, but it's important to know where everything is located. The eye wash is over there. Just pull the lever, and one will automatically turn on. To turn it off, just pull the lever back to its original position. community guidelines. If you get a spill on you, then quickly peel off your lab coat, and if your lab coat absorbed all the spill, then you're okay. If your clothes are contaminated, then you need to get into the shower and remove them under the running water.
Hey, seriously? I'm not taking my shirt off, so I'm gonna take pictures of people on Facebook. Don't be silly. It's not sticking to the book. Yeah, you're right. Flying up the time of the
In case of a fire, we have an extinguisher and a fire blanket over there. Use the fire blanket to smother a fire, especially if it's on someone's clothing. Or you can also push that person into the emergency shower and turn it on.
Kayla, can you show us how to use a fire extinguisher? I've never actually used one before.
In the case of a lab fire, it would be better if you evacuated the lab and let us worry about it. The safety of people is much more important than the safety of the equipment or the lab. And we do have fire sprinklers. But in any case, it's important to know how to use a fire extinguisher in the few cases where it might be needed. First, you pull the pin that locks the mechanism. Then, stand 6 to 8 feet from the fire and aim the nozzle at the base of the fire. A common mistake is to aim at the flames, but you need to aim for fuel. Squeeze the lever to release the chemicals and sweep it from side to side. An easy way to remember is the acronym PASS: pull, aim, squeeze, and sweep. Remember that if we need to evacuate the lab, then everybody needs to gather outside so that we can account for all of the students. And do you guys have any questions? All right. In this lab, we'll be working with various individual experiments, so make sure you read all the bottles of reagents carefully before you start using them, okay?
I always get confused about the order of addition. Is it water to acid or acid to water? I never understood it. It's easy to remember if you know the reason. The problem is that the reaction between concentrated acid and water can be very exothermic. When water is added to the acid, the reaction is so vigorous that steam forms. The steam escapes and will cause the expulsion of the concentrated acid. Adding acid into the water changes the situation. Since concentrated acid is denser than water, it sinks into the water and is immediately diluted. Now I get it. Thanks for your help.
Tanner, do we need DNA? Looks like we're just about out. I'll run to the stock room and get some more. Good morning, Professor. Yeah.
Hey, Adam, how's that going?
It's going pretty well. I'm just on my way right now to the stock room to fill the station call.
Okay. I think you're missing something. Let's go back in.
Okay.
Andrew, it's much safer to transfer bottles using the secondary container, because it offers better protection in case the bottle falls into us.
Okay.
Oh, and don't forget to take off those gloves before you do that.
Sounds good, Professor. Yes.
Hey, Nathan.
Hey, Professor, how are you?
Good. But why aren't you wearing your safety glasses?
Oh, sorry, they just caught up.
I know you didn't mean to do it on purpose, but what if your neighbor drops some dirt on a piece of glass goes flying towards you? It's pretty dangerous. You need to clean your safety glasses? Just go outside, clean them, and come back in. Also, I noticed you're working too close to the edge of the hood. This is not safe practice. Can I show you why? All right. Look at the dry ice spot. You see how it behaves when the dish is close to the edge? And especially when the sash is wide open? Now, think about all the hazardous vapors that will escape into the bag. However, pushing it into the hood about 6 to 8 inches and bringing the sash down makes a big difference. Plus, it protects from both hazardous vapors and flying debris if something goes wrong with the hood.
Thanks, Professor. All right, last.
Kate, this isn't very safe. Can you please sit down?
I know I'm not supposed to fill anything up by reaching above my eye level.
That's true. You definitely don't want to take a risk by spilling a solution from above. But at the same time, you may fall from this chair. A better way of doing it would be to move the burette to the side of the bench and then move it down so that you can do your work at eye level. Then when you're done, you can move it back up and push it back.
Okay, that makes sense. Thanks, Kayla.
You're welcome.
Oh, it's goodness.
Sorry, I was just wondering if I could borrow your calculator.
Yeah, sure, what was it? Go ahead.
Thanks. I don't think we're supposed to be listening to earbuds in the lab.
That seems kind of silly to me. I mean, not looking at the hood or anything.
Yeah, I know, it's kind of unsafe, like you can't hear what's going on around you, you might miss some things. Yeah, you're right. All right, I'll stop listening to them from now on. Thanks for looking out for me.
Okay, I'll bring it back when I'm done.
Yeah, sure, take your time, no problem.
Finishing up for the day?
Yeah, just keep it on my waist.
Alright, great. Do you know the proper way to take off your gloves?
Yes. And then pinch the first one, take it off, and use your thumb to take it off.
Perfect. Okay, well, see you next lab
See you
period.
next time.
You know, that wasn't so bad. Thanks all for your help.
Yeah, no problem, anytime.
I think it's all gonna be alright.
Okay, so gloves are required there. We don't have a requirement for gloves, but you should do frequent hand washing, soap and water. Even wearing gloves, I normally wash the gloves off just to prevent cross contamination. You know, with food and drink, like right now we're okay, but once we start, then you probably should put your food and drink away. If you need to take a drink, you can go outside, take a drink. We have the the safety shower again over there. There's an eye wash there, and then the handhelds. You guys are familiar with the handhelds? Yeah, from last time. Good. The sometimes you accidentally spill some. Like this morning, somebody spilled some oxalic or dichromate. If you do spill some solid there, get a damp paper towel and then wipe it off. Don't use a dry paper towel because it might create dust, but a damp paper towel should get it off, and then leave it in that plastic tray in which the waste bottle is located. I think that was it. Needed to say. All right, any questions? Oh yeah, one other thing, the hot plates. Normally with these hot plates here, you're going to get it to boiling. And so normally I turn it to max, but don't leave it on max because that could lead to splattering. And so if you turn it to max, you have to stay there and watch it because once you start seeing some steam come off, turn the temperature way down. Otherwise, there's a delay. It's not instantaneous how quickly those things change temperature. And then boil it for roughly 10 minutes. Yeah, individual. The report will be probably optional. You could work with other people on the report, but for the lab itself, let's see. Yeah, we want to see the crystals.
Biggest crystals win?
Yeah, the biggest crystals win a little prize. So let's see. The nicest crystals. You guys can vote for that. All right. So I guess I'll stop talking here. Probably when it's boiling, you can go pick up the filtration apparatus. You have to check that out. We have clamps. Buchanan funnels are top heavy. So we have utility clamps in the cabinet underneath the back bench there.